The other way to express this is a net loss of $5, getting your money back. Net gain of $5. You spent 5 and got 10 back, and net gain of 95. So like those are the different, there's 2 different ways to list the outcomes. But the probabilities of those outcomes are the same. So what are the probabilities of those outcomes? Well, ace of hearts, how many ace of hearts are there? 1 out of the 52 cards in the deck. How many other aces are there? Any other ace, so we already used the ace of hearts, so 3 out of 52 of the others. Any other heart, how many other hearts are there? 12. Which leaves how many other cards? Do some subtraction. So we've used 16 of the cards so far. We have 36 of them left. And if you want to simplify some of those fractions, you can. But what we're interested in is, should you play this game, we're going to get the expected value. Which is going to be, as we talked about yesterday, the value times probability of it happening. So our value here, our first value is 100 times probability, which is 1 out of 52, plus our next value is 10 times probability of 10, plus 5 times the probability of 5, plus 0 times the probability of 0. Ooh, 365. If you expressed this, I want you to compute another expected value. If you express the outcomes as 95, 5, 0, and negative 5, so if you used these values, (95) times probability of 95, (5) times probability of 5, and so on. Figure out what that is, and see if you can connect what each of these values tell you. Right. So, in other words, this tells you how much money you would expect to get back on average. This tells you your net worth after playing this game. And because either you could say this amount is less than the $5 you're paying, or this net outcome is negative, either way you want to think about it, it would not be advisable to play this game because on average, you are not expected to make a profit. This idea, if we have time. The only thing I'm going to mention here is that is this word of variance. Variance is a measure of spread, and I may have used this word before. If I haven't, variance is the standard deviation squared. So it is the standard deviation squared. It's even in the symbol notation, sigma squared. So if you want the standard deviation, and I have the variance, and I just want the standard deviation, then I'm just going to take the square root of my variance to get standard deviation. So to get the standard deviation, take the square root of the variance. Or in other words, if you want the variance, standard deviation squared. Right? And it's a big, long formula involving the expected value. You would take each of the values, subtract the mean, multiply by, et cetera, et cetera. I'll show this if I get back to it. The thing to know is that it's a measure of spread and standard deviation squared. We'll show computation stuff later. I'm putting it here so that you see how it works and that you can kind of parse it in the formula. But we'll come back to it. I want to get to some of the end of this stuff, which is talking about continuous random variables. A continuous random variable takes on all values in the interval of numbers. So a good test for whether something is continuous is whether you can have like a fraction or a decimal, if that would be a reasonable value. So before we were talking about discrete variables, where you had specific outcomes and only those specific outcomes. You couldn't actually have something like, you couldn't play that game from earlier that I was showing and make $25. That's just not an option. You couldn't make $5.15. Not an option. In continuous variables, you would be able to have all of the values in between, including decimals, including any of the numbers you could think of in that range, and have infinitely many possible values. So with continuous variables, because there are infinite possible values, talking about probability of specific values doesn't make sense. We only talk about ranges of values. So in normal distributions, that's an example of a continuous variable. And why we use normal CDF instead of normal PDF, because we're talking about a range of values. We have a lower and we have an upper. And so a normal distribution is an example of a continuous variable. We'll do this one last. I want to look at a new type of distribution here, which is called a uniform distribution. A uniform distribution takes in all the possible values and says that every outcome is equally likely to happen. That's why it's called uniform, because all the probabilities are the same no matter where we're at in the distribution. So a normal distribution isn't uniform because it has a peak and it has tails at the end that are less likely to happen. But a uniform distribution, everything is equally likely. So if we're thinking about like getting random integers out, having like a random numbers between 1 and 100, then in theory, every single number between 1 and 100 should be equally likely to come up. And that's what makes it uniform. Rolling a single die is uniform, because all the numbers 1 through 6 are equally likely to come up. Rolling 2 dice, not uniform. A 7 is more likely to come up than a 12.
What if you roll
So,
6 dice? Would that then go back to uniform?
huh?
If you rolled 6 dice, would that then go back to uniform?
No, not uniform, because some of, like, if we're talking about adding the numbers up, some of the outcomes are more likely than others. Now, the probability, because it's uniform and they're all equally likely, finding the area in a normal distribution, our calculator has to do it. In a uniform distribution, it's just a rectangle. So we're going to find the area of that rectangle to figure out what the probabilities are. Here we go. uniform distribution on an interval from 7.5 to 20 as a model for depth in the layer of sediment for a certain region. All right, so we're going to draw the density curve. And since it's a uniform distribution, our possible values, it says, are between 7.5 and 20. And all the outcomes between 7.5 and 20 are equally likely. Okay? Well, let's do area equals base times height. And the key thing here is that the area of a density curve has to be 1. Area underneath here has to be 1. And so what is the length of our base here? .5, because we're going from 7.5 to 20. So that length, subtract them, is 12.5. So if we want the height, this is part B. If we want the height, that tells us what our height has to be. It's got to be they got to be inversely proportional, is how you put it in Algebra 2 terms. So divide by 12.5 on both sides. And that's our height. We'll get decimals at the end. And our answer for part C and D, our answer for part C and D is going to be a decimal. On most questions, this part would just be the setup. And then the actual questions would be like part C and D. Part C. Probability that x is at most 12. At most means we're going to put what symbol here? It is less than or equal to. The largest possible value we can get is 12. So we get 12, or we get anything under that. Let's find the rectangle. Here's 12. I even stayed inside the lines. Isn't that good? All right. Base times height. Well, our height is going to stay the same, 1 over 12.5. What is our base going to be? We're going from 7.5 up to 12, so 4.5. And so our total area here is 4.5 times 1 over 12.5. So multiply that out. Zero point what? 36. Next. Part D. Probability. X is between 10 and 15. 10 is less than X is less than 15. Equals, well, here's 10. Here's where I'm going to put 15. There's our rectangle that we're interested in. So what's our base this time? Because our height is still the same. This time we're going from 10 to 15, so our base is 5. So 5 times 1 over 12.5. This should be a little bit bigger. 0.4. Specific values, I did put less than and not less than or equal to. But here's, I'll come back to that in a second. Here's the key part. Answer. Come on. What is it? Same thing. Why?
Because 12 and 17 have the same distance.
Same width. So the rectangles are congruent, to use our handy geometry. Because our width is also 5, our base is also 5, and our height stays the same. And so it's going to be the exact same probability. Again, doesn't happen in a normal distribution because our height doesn't stay consistent throughout. But it does here.